Okay, so for the warm-up today, again, we talk about the first few problems. It talks about exponential growth versus decay. So we talked about these numbers in here. And you might remember the general form we used was y equals a times b to the x. And we said if the b value is bigger than 1, then we're talking about exponential growth. And then we said if the b value is between 0 and 1, then we're talking about decay. And then if the b value is negative, it just doesn't work. That's what we talked about. A couple classes ago now. So that's why I'm bringing it back up today, just trying to refresh our memories on it. So now the first b value is 2, so problem 1 is an example of growth. The second one is also 2, so that's another example of growth. It doesn't matter what is happening in all the other numbers. The only one we're looking at is the one that's being raised, the base of the exponent. Only number we need to look at. And the last one's 0.8, a number between 0 and 1. So that's a good example of decay. That's what the first 3 problems look like. For the next problems, I'm going to give you a little more time on them. But first, just a reminder, like the first one's like 2 to the question mark equals 32. So we got to ask ourselves, okay, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32. So that's what we're looking for, is something like this. Okay, well 2 to the fifth is 32, so that means I can substitute 32 and rewrite my logarithm in terms of 2. That's the goal for these ones. And now I can use the properties of logarithms to simplify this expression. All right, so take another minute on these other 2 problems, 5 and 6. All right, so just to go over these now, we've got this log base 2 of 2 to the 5th power. So technically the 5 would drop out front. You're left with log base 2 of 2. And log base 2 of 2 we know is just 1, so this is really just 5 times 1. That's why we were trying to get it in terms of 2, because once we have it in terms of 2, we know that's going to simplify to just a 1. And 5 times 1 is 5, and that's our result for problem 4. For problem 5, we would do something very similar. 3 to the question mark equals 81. Do something with that base. Problem 4 would be 4 to the question mark equals 2. I know 3 to the first is 3. 3 squared is 9, 3 to the third, 27, 3 to the fourth, 81. Okay, so now I can say, this is going to be log base 3 of 3 to the 4th power. That's the exact same way of writing 81, just with, in terms of 3 now. Drop the 4 out front, 4 times log base 3 of 3, so this one simplifies to 4. Last problem. 4 to the question mark equals 2. Well, if I did that same method, or I say 4 to the first equals 4, 4 squared equals 16, I'm already way past 2. So this is one of those ones where we have to kind of go the other way. We don't want bigger numbers in the exponents, we want smaller numbers in the exponents. And the way we go to smaller numbers in the exponents is we have to think about like, square rooting. So remember, like square root of 4 is 2. But we could also write square root of 4 as a fraction. That's 1/2 power. So 4 to the 1/2 power is the same thing as 2. So for this problem, we could say log base 4 of 4 to the 1/2. And now I've got the logarithm in terms of 4. I drop the 1/2 out in front. And I've got 1/2 times log base 4 of 4, or just simply 1/2. That one's definitely the trickiest one of those 3. But that's the idea for evaluating these logarithms without a calculator. You want to think about, how do I look back at exponential form and figure out what this exponent's going to be. Okay, done. Let's go ahead and start talking about our lesson today. Oops. So what we're going to do is we're going to talk about applications. So exponential and growth models. First time we really get to look at these from an applications perspective. put our date today, so if we ever need to go back and look at our notes, like what was Mr. Street talking about, you can find the right day posted on our Canvas page and refer to the video notes. All right. So exponential growth models, when a real life quantity increases by a fixed percent during a fixed time period. Whenever we're talking about time periods here, remember we have to specify which time period, because time period could be hours, centuries. Most commonly it's going to be years when we're talking about certain problems, but it really depends. The amount y of the quantity after t units of time can be modeled by this equation. So let's break down what this equation is telling us. We're starting with this a value here. The a value is going to be our starting value. It might be the initial amount. It might be a principal value. We're going to call it a few different things. So initial amount, that's our a value for this type of equation. We're going to break down what this equation means exactly. The next thing we have is this r value. R is the percent increase all right, and we always want to write it as a decimal. So if I tell you something's increasing by 98%, you're going to put it as 0.98. You don't want to put it in there as 98. That will give you the wrong answer. So whenever you're using this equation, you have to keep that in mind. T, that's time. And we have to specify what time is, because you could be talking about seconds, minutes, hours, days, weeks. But years is usually the most common thing we use when we're talking about time. We've got the y value, and y is going to be the final amount. So we start with an initial amount, and y is our final amount after we run our calculation. And then the last thing we have here is this 1 plus r. And 1 plus r is the growth factor. All right. And in order for it to be a growth factor, it must be larger than 1. All right. And again, growth factor, because we think about that equation, y equals a times b to the x, and we're saying in this case b is larger than 1. That's what makes it the growth factor. All right, so if you're taking some interest rate that's a number smaller than 1 and you're adding 1 to it, you're going to end up with a number bigger than 1. All right, or not the interest rate, but the percent increase. Yeah. All right, and we'll take a look at our first example here. Example 7 says, in 1996 there were 2,573 computers, or computer viruses, and other computer security instances. During the next 7 years, the number of incidents increased by about 92% each year. Okay, so write an exponential model, exponential growth model given the number n incidents t years after. So when we see the number n incidents, that's really the y value. So those variables will change from time to time, which could make things a little bit confusing, but hopefully it's not too bad. I'm just going to write it out real quick. It's going to be n equals, the initial amount was 2,573, and our rate, again, it was 92%, so we need to write that as a decimal. Think if you had a point there, you move it over 2 spots, 1, 2, so it becomes 0.92. Or you divide 92 by 100, which would also give you the 0.92. So this becomes 1 plus 0.92 to t. In this case, we'll just leave it as t for now. But that's what our model is going to look like here. Or we could simplify the 1 plus 0.92 a little bit if we wanted to. 2573, 1 plus or not 1 plus 0.92, we'd say 1.92 to the t. And when we have that 1.92, now we can see this is a growth factor right here. That's a number bigger than 1, so this is definitely going to be growing. It says, use the model to predict the number of incidents in 2003. A common mistake with this type of problem is when people see 2003, they think, oh, I'm going to put 2003 in for my time. But that's not correct. Because 2003 is actually, we're starting in 1996, so 2003 is actually 7 years after 1996. So when we plug this equation in, we're going to use 7 for the t. And we should be able to run our calculator and come up with a calculation for how many viruses there are now. And it comes out to like 247,484 point something something something. And I'm just going to round it. Round to the nearest whole virus or whole number. Okay, that's the idea for this problem here. I'll scroll back up just a little bit here. Sorry, I scrolled down a little bit too much. Hopefully you can see that there. All right, so what we're going to do next, we have this. We're going to graph this model. And I'd recommend doing this on a graphing calculator. Really important that we know how to read this on a calculator. Or we could graph it on Desmos. I'll show you how to do Desmos right now. It's the same idea as a graphing calculator. But in order to use a graphing calculator, you're going to want to use X instead of t. And we would just write this as y equals 2,573, 1 plus 0.92 to the x power. That's what our equation would look like that we want to put into the graphing calculator. Or we could do 1.92. It doesn't have to be 1 plus 0.92. But let's go and switch to Desmos screen now. After we graph on Desmos, we come back here and we'll say, okay, important thing, I want to check my viewing window. And make sure it works in the context of the problem. I mean, once I zoomed out and got the right context, it looked like an exponential growth model, but it looked really weird when I had the wrong scale on there. When I used the graph to estimate 125,000, I wanted to find X years. And I found about X equals about 6. Whoops. So the year would be 1996 plus 6. 2002 would be our final answer. Okay. And I should be able to do this algebraically as well based on what we've done now. We could have said 125,000 equals 2,573 times 1.92 to the x. And then we just divide both sides by 2573. All right, and we'll get some weird number. .48. So we get something like 48.58142246 equals 1.92 to the x. And then we can log both sides. And the x will drop out front, and we get log of 1.92. And then we can divide both sides by log. So we'll do log of this answer. I'm trying not to round because I want to keep this as accurate as possible. And we know how to solve this algebraically, which is nice for us. And it comes out to 5.95. We get the same answer solving algebraically, but we can verify that on our graph. That's what's really important about these graphing problems. We can do it both ways now. Okay. That was kind of a lot with that first real world example. But we should be able to do graphically. We should be able to solve it algebraically. We should be in good shape on these types of problems. But this homework assignment tonight is going to be 4 real-world practice problems, and we're probably going to see a real-world problem on the test next week. Not next Tuesday will be our test. So just so you guys keep that in mind as we're getting ready for the next week or so. And since we're all good with questions, we'll move on to exponential decay models. And exponential growth and decay, those equations look very similar. The big difference here is there's a minus here instead of a plus. Everything else is the exact same. The only thing that's different is that minus sign instead. And what that minus sign is telling us is R is now the percent decrease. It was the percent increase in the growth model. Now it's the percent decrease. That's how you can tell the difference between an exponential growth problem or an exponential decay problem. And again, when we're doing percent decrease, we're going to write that as a decimal. A very common mistake I see from students is they forget to write it as a decimal, and they get the wrong number. And then we have this 1 minus r. That is our decay factor. And again, because that's like kind of the b value, and that b value is going to be between 0 and 1, which shows us this is definitely exponential decay. All right. So this example says a new snowmobile costs $4,200. The value of the snowmobile decreases by 10% each year. Write an exponential decay model given the snowmobile's value in Y dollars after T years. So we'll start with the model. We'll say Y equals, the initial amount was $4,200. 10% we could rewrite as 0.10. We just move the decimal over twice, or you divide 10 by 100 to turn a percentage into a decimal. So 1 minus 0.10 to the t, or if we do that subtraction, we would just get 4,200 times 0.9 to the t power. And I like that 0.9 to the t because now I can see this is definitely a decay problem because the number here is smaller than 1. All right, a lot easier to see after we complete that subtraction. All right, so this first problem says estimate the value of the snowmobile after 3 years of depreciation. So 3 years is going to be when we put 3 in for t. What's the value of the snowmobile after those 3 years? So go ahead and put that in your calculator. All right, and we'll figure out what that number is. And what happens is we get 3,061.8. But we're talking about dollars. So I don't want to leave it as 0.8. I want to add this 0 as well. And that's because with money, we always round to the penny. So even though in this problem it ended up being 0.8, we'll add the 0 and say this is $3,061.80. All right, it's really important that we do that. Whenever we're rounding money, we should round to the nearest penny. All right. Now for this one, it says graph the model and use the graph to estimate when the value of the snowmobile will be $2,500. What I'm going to do instead is I'm going to give you the option. You can go back to Desmos and you can graph it, or you can solve it algebraically. And personally, I think even if you solve it algebraically, you can double check it on a graph. But I'm going to give you guys a couple minutes to solve the problem right there. All right, so after we work through some numbers here, we should see that t equals about 5 years. So it'll take about 5 years for this thing to devalue to about $2,500. And again, if you're using a graph, you got to know how to work that scale. The y value starts at 4,200. So you'd probably want to put your years from about 0 to 10. So your x-axis 0 to 10-ish. And your y-axis, you're probably going to want to go from about 4,500 down to $0. Something like that, so you could see the exponential decay over time and what's happening to this problem. All right. Any questions on this problem before we move on to the next one?
For logging.
So let's take a look at the next one. This one's compound interest, which compound interest is really cool if you are good at saving money. It's really bad if you're good at spending money. So you just have to make sure you're on the right end of that one. Compound interest is killer for people that have credit card debt, because that's how interest is calculated on credit cards, is it's compounded. And we're going to talk about what that means. So compound interest is interest that's paid on both the initial amount and previously earned interest. All right, that's compound interest. The initial amount and previously earned interest. So very similar equation to what we saw before. We start with P. That's the principal or the starting value or the initial amount. All right, that's always going to be the same thing. It's the number that's outside the parentheses. R, that's the interest rate again. Well, in this case, it's going to be the interest rate. It's the annual rate. Okay. T is still going to be time. Oops. Except now we're talking about time in the number of years specifically. So whenever we're doing compound interest, T is always going to be the number of years specifically. A is the final amount, just like it was before. And the only new thing we have here that wasn't in the previous equations is now this N that shows up at two separate spots. And N is the number of times your interest is compounded per year. So whenever you're doing a compound interest problem, you're going to know how many times it's being compounded per year. Okay. Let's take a look at an example and we'll make some sense of this equation. But it's very similar to the other one. We're just adding this N in two separate spots. Everything else is going to be the exact same. All right, so for this example, it says you've deposited $4,000 into an account. Good for you. That's awesome. That's a lot of money. And you found this interest account that's going to pay 2.92% interest. So 2.92%, if we want to put that as decimal, we're going to move that 2 spots. So there's actually a 0 there. So it's going to be 0.292. So 0.0292 is going to be your rate that you're going to use. Always turn that into a number, a decimal. Don't leave it as a percentage. All right. When we write the equation now, it says, let's do this for 1 year. So we'll use our t for 1 year right now. And when we write this equation, we'll go ahead and start by saying A equals our initial amount, our starting value, $4,000, 1 plus, and then we have this 0.0292 over, and we don't know what n is yet, and we're going to say the 1. So that's where our t value comes in. There's our time, our rate, and our initial amount. And then the last part, it says it was compounded quarterly. So how many quarters are in 1 year if it's compounded quarterly? Think about quarters in a dollar. It's the same idea, right? You should end up getting 4 when you're doing this for quarterly. And what we're going to do is we're going to calculate this interest rate for each of these scenarios. Except on this one, we're compounding monthly. How many months in a year? 12 months in a year. And this time it's 12 times 1, so it'll just be 12 to the exponent as the exponent. We compound daily. What happens if we compound this amount every single day for 1 year? And this year we had 365 days. Or 366 days, but a typical year is 365, so we'll just leave 365 here as our yearly amount, times 1. And then the last one, what happens if it compounds every minute? What's that do to our value in the account? And if we did every minute, you have to think there are 60 minutes in an hour, there are 24 hours in a day, so I'm going to do 60 times 24. And there are 365 days in a year. So I have to put how many minutes per year there are. And there are 525,600 minutes. All right. And we're going to see which one of these compounding methods is going to have you get the most money after 1 year. All right. Anyone have any guesses which one's going to give them the most money after 1 year? Guesses at all? Nothing? All right. So go ahead and put those in your calculator, see what we get. All right, so when we put all these into our calculator, this is why it's really important that you guys know how to put it in your calculator. Whenever we're compounding with different numbers, it's really important to note that the value is not going to change by a significant amount. Like if it's $4,118 on part A, it's not going to be $4,562 on part D. It's got to be very similar. So the compounding interest does help. It's going to make things a little bit better the more it compounds. But I mean, look at the difference is like 9 cents versus 52 cents. All right, that's just after 1 year. But now, if you're doing this for like 7 years, it's going to make a much bigger difference, but the difference will still only be a few dollars. It's never going to be something where it's like, I made $4,200 versus I made $7,000. That's not going to be a huge difference unless you're talking about a really high interest rate over a long period of time. All right. But what we're seeing is in 1 year, if you found this account that has 2.92% interest rate, you made $118.09 for doing nothing if it compounded every quarter. If it compounded every minute, you made $118.52 in 1 year for not doing anything, which is pretty cool. Either way, you're up $118. That's why compound interest is great. It's going to help you make some money for doing nothing. All right, you just have to have that money in the account, let it sit there, and work its magic. All right. Credit card debt's the same way, though. I mean, if you don't pay off your credit card, then they're going to charge you their interest rate, and it's going to compound every month. So if you don't pay that credit card, the next month it's going to be even more. Okay. Okay, I got a practice problem here. It says at an online auction, the opening bid for a pair of inline skates is $50. The price of the skates increases is key, by 10.5% during the per bid during the next 6 bids. Write a model given the price P in dollars of the skates after N bids. So for this one, you think about which equation you're going to use. I'd probably stick to the very first one we did. And now I'm going to ask you guys to go ahead and write this equation with the numbers in it for part A. So write the model with the numbers in it, plugged it in the right places. And then go ahead and work on parts B, C, and D. Take a couple minutes to work on that. So after we do our calculations here, we end up getting like $82 for 5 bids, but then like over $1 million for 100 bids. And this is for a pair of inline skates. So it's either the predicted price is reasonable, right? I mean, some of us could argue, no, neither one's reasonable because they're inline skates. But I would say $82 is definitely reasonable. I mean, you're going from $50 to $82 and it's a bid. So that seems like a reasonable price. Now, $1 million, that seems very unreasonable to pay for a pair of skates, unless they're Beyonce's or something. But otherwise, I would say completely unreasonable for paying that price for something like this, like a pair of skates. All right. So we're going to do tonight, I'll save the natural base E for our lesson on Thursday. And we'll talk about this stuff on Thursday, the continuously compounded interest and stuff, finish this lesson off. But your assignment is 4 problems, and it shouldn't require anything from the rest of the lesson today. So I think you'll be okay using this. But 4 real world problems I want you guys to give a try, and we'll work on these on Thursday. For tomorrow, I'm going to have you log into Canvas, and then you're going to complete a quiz on Alex. So you got to link through Canvas to get to the Alex page, and I'll have instructions posted on how to do everything. But that's our goal for tomorrow. We are going to be taking our test next week on the Alex platform. So tomorrow is like a practice quiz to try and get you ready for that. So you can be familiar with the platform, and then also if you have any technology hiccups, I want to know about those so I can get those fixed for you before our test next Tuesday. All right, but that covers everything we have today.